Good morning, everyone. We are ready. I'm very excited to have you all here today and for what will be an amazing day of AI. My name is Rada Mihalcea. I'm a professor of computer science here at Michigan and also the director of the AI lab. And on behalf of the Michigan Artificial Intelligence Lab, I'm pleased to welcome you today for our 6th annual symposium. The AI lab at Michigan is one of the largest academic labs in the world and also one of the labs with the longest history. It was founded back in 1988 when a group of faculty got together with the goal to advance AI at University of Michigan. Since then, we have come a very long way. And now we are a group of 25 faculty, 100 PhD students, many undergraduate, master students, postdoctoral fellows who work across all areas of AI in machine learning, computer vision, natural language processing, robotics, and more. We also have a growing number of alumni who are making a difference across the world, both in industry and academia. And we take a lot of pride in forming strong collaborations across all disciplines, also in working closely with our industry partners, again, across all areas. And we also take a lot of pride in facilitating the exchange of ideas with all of you, like we do here today. So with that, I'm very happy to welcome a wonderful guest today, Provost Laurie McCauley. Provost McCauley has been appointed in her role in 2022, and since then she's been overseeing Michigan's rapid, impactful expansion in generative AI, where Michigan became one of the leading institutions in this space, not only in terms of research advances, but also in terms of a tight integration of generative AI with our research, education, and societal mission. I periodically get emails from colleagues who are at other institutions that are seeking to replicate what Michigan has been doing and asking me, how does Michigan do it? Just to give a few examples of the work that under Provost McCauley, we've been seeing at Michigan over the past 2 years. In 2023, there was a generative AI working group that has eventually wrote a report that's now widely referenced on the use and implications of AI in higher education. We also have GPT models available on campus to everyone. And not only that, we also have started for a little more than a year, the Hejie suite of tailored solutions in AI. Some examples from that is the Hejie AI Tutor, where an instructor can customize an AI system for their class, essentially offering 24/7 support to their students with material from their classes. Also, the My Hejie personal AI assistant that has knowledge about University of Michigan, including dining hall menus, the academic calendar, campus mental health, and more. And the list goes on with the initiatives that Provost McCauley has overseen, so I'm really happy to have her join us today.
Wow, what a delight to be here. I guess, having a humanoid provost is a letdown after, after this type of greeting. But welcome to the University of Michigan. Really, it's my pleasure to be here for what looks like just an amazing AI symposium. We're joined by AI researchers, leaders from industry, academia, teachers, engineers, and robots. And many more people who are just curious about artificial intelligence. And in fact, who isn't curious about AI now? What a really exciting time it is to be in this field. So welcome to all of you, and I hope you'll just really enjoy the day today. Well, we're living in an era where leaders could give remarks that they didn't generate themselves. It could have been generated by GPT. I'm here to say that I did not use U of M GPT to develop these remarks, but I actually yesterday had a colleague who's invited me to give a talk in the spring, and she gave me a whole list of GPT-generated titles that I could choose from for my presentation. So let me just share with you one author thinking about issues that we may be talking about today, and I'm going to quote this, quote, "A very special device that would allow anyone at a reasonable charge and with a little bodily labor write books in philosophy, poetry, politics, law, mathematics, and theology without the least assistance from genius or study." So in this story that I just clipped a little bit out of, that type of work of generating these books was done with an iron handle, basically, cranking. So you might say that sounds kind of like our large language models, really just kind of cranking out work. But in fact, this was a paragraph that was written 50 years before the United States was founded. This was a wondrous machine that was encountered by a man named Gulliver during his famous travels, as detailed by Jonathan Swift in his famous novel from 1726, and is thought to be one of the first descriptions of the modern computer. In fact, last year, something like the device described in Gulliver's Travels became easily accessible to anybody with an internet connection. It immediately changed the way we think about writing. It also catapulted AI into the public consciousness in a profound way. And as Rada referred to, here at the University of Michigan, we chose to really lean into this. And I can say, because of my travels to other universities and around the country, we absolutely led the way in providing these tools to our community. And I have to thank partnership with Ravi Pense and his team in the CIO's office at the university, because as Rada highlighted, we debuted U of M GPT, our in-house generative AI model for students, faculty, and staff, all having open access without charge, and yet with a privacy envelope. We also provided Hejie, a tool that allows the user to load custom data sets to extract insights and discover patterns. And our instructors have just really taken this up, and it has provided a 24/7 tutor for students in their classes. And as she also said, last month we launched My Hejie, which is a personal tutor for students. It hooks their personal questions, interests into Canvas, into their coursework, and provides them to engage in natural conversation, asking questions about our university experience. Well, of course, AI is much more than large language models, although that has been really an attraction of late. But in the last few days, AI discovered hundreds of new geoglyphs in the Peruvian region of Nazca. And it was announced that AI will replace human line judges in next year's Wimbledon championships. In fact, there's no domain of human knowledge that doesn't overlap in some way with artificial intelligence. If you ask moral philosophy, well, we could have an entire conference about the intersection between AI and ethics, and there's a lot of people on our campus that have engaged in this. Whether we're talking about sentience, how machines make decisions, and the data that we use to train them. The same goes for art, pedagogy, psychology, and every medical science. Whether we're talking about how behavior develops, the mechanics of language, or the role of human labor in society. We are living in unprecedented intellectual times. And basically what I just described to you is giving a nod to all the things that you're going to hear about today. I also just want to highlight that the work done on our campus has been long-standing, and we have been leaders in this area. As Rada mentioned, the AI lab going back to 1988. It's home to world-renowned AI researchers and the hub of core AI research on our campus, and we're really fortunate to have Rada Mihalcea as our passionate and brilliant leader of the AI lab. So thank you, Professor Mihalcea, and your entire team for your revolutionary work. Special thanks to Stella Yu and Andrew Owens, our AI Symposium co-chairs, for putting together such an amazing event. And thank you to all our speakers from campus and abroad, and our robots for their presence here today. I know you're going to enjoy this symposium and look forward to hearing about the success of today. So again, welcome to the university. And with that, I'll hand it over to Stella.
Welcome, everybody. This is the 7th AI Symposium. And this year's theme is Embodied AI. And I'm Stella Yu. I'm a computer vision researcher and professor at University of Michigan.
Oh, I'm Andrew Owens. I'm computer vision faculty also at University of Michigan.
This year, we have the largest attendance. We have 500 people registered, and we have 11 company sponsors, 3 keynote speakers, 4 guest speakers, and 6 rising stars, 63 posters and demos. Compared to last year's Responsible AI, we have 150 more people. You know, this is the largest attendance since during COVID we had larger attendance, but that was online. So we are back to normal, and we are so happy that everyone can make time to attend this symposium. We are very honored to have 3 keynote speakers: Karen Adolph from NYU, Dieter Fox from University of Washington and NVIDIA Robotics Research, and Jitendra Malik from UC Berkeley. We have 3 types of speakers. On your printout, there's keynote speakers, and 4 guest speakers, and the rising stars marked by this lightning sign.
I'm particularly excited for the poster and demo session. That's going to happen around lunchtime. And associated with that, we have a bunch of different awards for different best poster and so on. And we're going to show it again, but there will be a QR code you can use to vote for these different awards. I also want to mention that at the end of this, around 5:50, there will be 5 meetup opportunities. And if you'd like to meet up with people and get dinner, you can join folks there. The people who are part of the AI lab, the speakers, you'll just come to the front of the stage and we'll take you to that dinner as well. I also want to thank all of the people who went into creating this. In particular, I want to thank Daniel Gang and Zilin Wang for being the poster and demo chairs. All the student volunteers who did so much. They did everything from setting up tables to helping with registration. Really, really thankful for all of their help. Don Windsor, who you'll see throughout the day, providing all the tech support. Also thank Unitree and Stokes Robotics for setting up these robots. Aurelia for the artwork and the social media. And last but not least, Christina Serto, who really has done so much behind the scenes to set this up, has been really leading the way here. I also want to thank all of our industrial sponsors, and as well as the robotics companies who have, like Unitree, who have set up these demos. And also I want to thank, of course, the Computer Science and Engineering Department for also funding and supporting this. And so I'll hand it off to Stella to introduce the next session.
So let's get started with the first technical session. And the first speaker is our first rising star from Harvard. She is a PhD student there, and she's working at the intersection of human-AI interactions and responsible AI. Her work has been recognized by an IBM PhD fellowship, rising stars, multiple rising stars, and a Siebel Scholar. And most important of all, she is named as one of the top 10 stars in STEM in Kosovo. Most influential woman. Okay, please welcome Zana Bucinca.
So I am Zana Bucinca, and what I ask is, how will AI assistance affect what we value about our work? So AI assistance is transforming our workplace and the tasks that we do, but how it will affect what we value about our work. Most of the current existing tools and research focus on the tangible output of human and AI decision-making, such as how can AI assistance improve decision-makers' accuracy or efficiency. However, as these tools become integral part of our tasks, work, and workspace, I think that they will more increasingly affect values beyond the output of our work. They will affect our skills in the tasks that we use them, our agency that we have in our decision-making, the meaning of the tasks that we carry when half of the task is done by an AI, and whether we collaborate with others. I ask with my research, how can we optimize decision-makers' values, both human-centric and output-centric values in AI-assisted decision-making? I frame this research as value-aligned interaction because I believe this is an interaction problem. Different from the research in value alignment about AI, which focuses on the AI alone. So this discourse and research around value alignment focuses on developing AI whose predictions, generations, and overall kind of outputs are in line with norms and with the norms and values of society, such as being fair, being transparent, preserving privacy, and so on. However, once these models are output and deployed in the world, they interact with humans whose values we're not accounting for, and new values emerge from these interactions. Like, how will people's skills be affected in their writing as they use GPT for writing? Or how will we actually know how to code? What will happen to the agency of the decisions that we make with these systems? In the first part of my talk, I will focus on the output-centric values. Essentially, how can we optimize the accuracy of human and AI decision-making? I focus and am mostly inspired by high-stakes clinical decision-making contexts, but this research is broadly generalizable to other domains. So think about a doctor who gets, like, this is the current way that people get AI decision support, where a doctor is given a decision about a patient and they receive an AI recommendation about what to do, which is often accompanied by an explanation, which can take form of a feature importance, but can also be a natural language explanation. This simple explainable AI paradigm was thought that, hey, as explainability and interpretability researchers, we were excited that we are allowing the human to see where the AI can go wrong and the human can override the AI, right? Because like they can see the AI's explanation. And we expected that human and AI's team will perform better than humans alone and AIs alone. However, in reality, this is not what happened. hundreds of empirical works show that when people are tasked to work with AIs on decision making, they perform better than humans alone, but worse than AIs alone. In a study, we looked at this deeper, and we saw that when the AI provides a wrong recommendation, people over-rely on it, even when they can make a better choice on their own. But we asked, why do people over-rely on AI to begin with? We looked at this through the dual process theory of cognition, and we hypothesized that when people receive an AI recommendation, they're essentially getting a shortcut to a decision so that they can heuristically rely on the AI, whereas evaluating explanations and recommendations requires cognitive effort that people may be unlikely to exert. Therefore, we said if people can be induced to engage analytically with AI recommendations and explanations, their over-reliance will decrease. To do this, we introduced cognitive forcing functions as interaction interventions. So we did not interfere with the model, we just interfered at the interaction level, which allowed people to form an initial hypothesis about a decision before giving them a recommendation. This would be like people could make a decision on their own first and then see the AI's decision. They had an opportunity to wait before seeing the AI's recommendation, or they could click on a button to demand the AI's support. Our results showed that people's over-reliance was significantly reduced with cognitive forcing functions than compared to simple explainable AI that just gave people the solution. However, this came at a cost. People hated these interactions. Since our work, other new techniques are being developed to push people to engage more with AI support, like giving them explanations without recommendations, or explanations framed as questions, or even evaluative AI that evaluates your decision once you make one. However, growing evidence suggests that the type of interaction, the suitability of interaction depends on the objective of the interaction, the individual, and the context. Therefore, we asked, how can we decide which kind of assistance is best for whom and when? So can we push people to think only when it is necessary for them to think more? So we framed this as a reinforcement learning problem where the RL's agent's goal is essentially to choose what type of support to provide to a person given the state of the interaction. For example, should we provide them full support, partial support, or no AI assistance? We constructed the state based on the human and AI dyad, like whether the AI is uncertain, whether the person is motivated to think, and their skill on the task. So we had people complete repeated decisions, and we provide a different form of support. From this exploratory policy, we optimized policies to improve accuracy. And our results showed that with people that interacted with accuracy-optimized policies achieved significantly higher accuracy than those interacting with any other form of AI support. They even achieved human and AI complementarity. And people also liked the interacting with these policies. So going to the other branch of my work, in a very recent study, we focused on can we improve people's skills as they are interacting with AI. So essentially, as you're using, for example, GPT for coding, can you get better at coding as well? We looked at this in decision making because the evidence suggests that when people use AI support that provides solutions to them, they do not improve on the task. And there's evidence that they may even get de-skilled over time. So we asked whether we can design support that both enhances accuracy and people's skills. We hypothesized that what people ask from the AI is to provide the delta, essentially the knowledge gap that they have from what the AI is saying and what the human thinks, which is like a contrastive explanation, whereas what the AI provides is unilateral explanations from the AI side. Essentially, AI suggests a choice and justifies its decision, but does not consider humans' thinking. So we built a framework in which we modeled the human, and we tried to predict what the human would say, so essentially the human misconceptions about a task, and we generated these contrastive explanations that explained the difference between the AI's thinking and the human's thinking. Our results showed that people that interacted with contrastive explanations significantly improved learning compared to these unilateral, which is the standard way of giving people explanations. So if we consider the human's reasoning when we provide support, we can improve people's skills on the task. So to sum up, I showed you that there's a lot of, I think, innovation to happen in the interaction layer, where we can choose what to optimize. Essentially, accuracy and skills were the two values that I considered here. How to intervene, the type of support that we can provide to people to optimize their values, and also how can we design the interaction layer so that we intelligently provide the support at the right time. So, thank you.
Let's take one quick question.
I love this, but isn't it a lot like just being a good teacher, a good mentor, a good caregiver? If you take the learner's view into account.
Yeah, exactly. So do you mean for the contrastive explanations part? Yes, exactly. So this is like all informed by research in philosophy, and also like the causal, some kind of people ask for contrastive explanations, and the theory of mind aspect of it. When people provide explanations, they also want to reach at that delta between, you know, what the explainee is seeking versus what the person that explaining is providing. So, yeah, thank you.
So while Joyce is setting things up, I'll introduce Joyce. Joyce is a professor in CSE at University of Michigan. She has won many Best Paper awards, and most importantly, she has won Alexa Symbol Challenge last year. Her work aims to enable situated communication between embodied agents and better human-AI interactions.
So it's really great to have all of you join us here today for this exciting symposium. So embodied AI is AI agents that can interact with the physical environment and can learn from perception, action, and communication. When we talk about embodied AI, what comes to mind is this cognitive robots. And cognitive robots are other robotic agents that have higher cognitive abilities. And it's dated back to 1960s. For example, here, this is the Hejie robot from SRI and Cog robot from MIT. Okay. And more recently, we have seen really unprecedented excitement in cognitive robots. And of course, we just seen these Unitree and Stock robotics on the stage. So as a language person, I have been always fascinated by language use in physical context. What has been in my mind in the last decade is how to enable language abilities in these embodied agents, enable them to communicate with humans in language. So humans are not the only species who use language. Any animal, have some sort of language to communicate with each other. Like ants and bees, they actually have some sophisticated way to communicate with each other. But to unlock human language communication, researchers have studied communication between primates because they share same ancestor with us tens of millions of years ago. And for example, in this work published as Science 1980, researchers found that these vervet monkeys, these are the monkeys from East Africa, they can make distinctive alarm calls to indicate the presence of 3 different predators. So the the monkeys who hear the leopard calls would run to the tree, and the monkeys hear the eagle calls will look up and run to the bushes, and the snake calls will look down. And researchers found that even there isn't any predator present, when they play the recording of these alarm calls, and the monkeys would still select the appropriate response. So this alarm call has been viewed as one of the first examples of symbolic communication in non-humans. And what really interesting here is also that when adult monkeys made these calls primarily to leopards, eagles, or pythons, but infant monkeys make these leopard calls to various mammals, eagle calls to many different kinds of birds, and snake calls to very snake-like objects. But the ability to identify these different predators and also issue these appropriate alarm calls improve with age and experience. So this is some way show the evidence of embodied experience shapes the learning of language communication. In fact, historians and anthropologists tell us that our early primates, they already developed some visual abilities that allow them to navigate the complex physical world, avoid predators, and seek food. And this has been going on for tens of millions of years. And the language did not appear until quite recently, 70,000 years ago. But what happened is that when this language appeared, human history experienced this fast, unprecedented transformation. So this is called cognitive revolution. So language, this is when the Homo sapiens, they start to think, start to communicate, and understand the world. And the language plays a really important role here because that allows Homo sapiens to transmit information about their surroundings, allow them to plan for complex actions, and they can share knowledge, experience across generations and facilitate, accelerate learning. So the emergence of the language empowers human intelligence. And not only through the history of the human history, it also, this trajectory is manifested in the lifespan of our human development. So Karen is here. So when the children start to explore the world by touching, smelling, listening, moving around, and by 12 to 18 months old, they start to speak the first words, connecting that with the shared experience, what they see, objects, people, and so on. So abundant researchers have really shown that the language learning is deeply intertwined with the physical interaction of the world. And once we have the language, we can communicate, then that allows us to learn new skills, to collaborate, to engage in complex social activities. So again, language use empowers our intelligence. And the researchers have also looked at different various pathways that bring the experience, language, and the intelligence in this virtuous cycle. So my lab our mission is to bring humans, agents, and the world together to explore these pathways with a particular focus on language. And we're very excited about two directions. One is how embodied experience shapes language learning, and the other is how language use powers embodied intelligence. So in this talk, I will sample a few stories about our recent work exploring these directions. So the first story is about embodied experience shapes language learning, and I will focus on the word learning that is grounded to the perceived world. So I start with an example. So suppose you have this picture and you have this snippet. A lady wearing a navy blue striped tank top is getting ready to burn glass in front of an incinerator. So suppose you know the lady and the tank top glass, you know what they're referring to in this image. And now suppose that this incinerator is some new word you don't know what it refers to. But you can have a pretty good guess that this refers to this apparatus in the background in this yellow box. So what happens here is we humans, we have the ability to use what we know and their connection with the environment, the visual context, linguistic context, to allow us to do this mapping. So this is called fast mapping, learning new words with only minimum information. So then the question is, how do we enable AI agents to have this fast mapping ability? So this work is a joint work with my student Martin and Hejie, and we formulated this problem as an open vocabulary acquisition problem. So what we're looking at is during the pre-training, the model acquired this grounding ability. Can this grounding ability to allow the agents learn unseen or new words without grounding supervision through a few examples? And so more formally, given a sentence, given a picture where a word is masked out, the goal is trying to predict this word and also connect that with the corresponding boxes in the image. And I don't have to go through this model, pretty typical model, dual stream model here. But we have this objective at mask language prediction and object localization. And we also have this objective of grounding, essentially task model to really align words with their perceived object. So we can compare models with grounding and without grounding objective. And we have a bunch of results, but in the interest of time, so I only show one result here. This shows the training steps. And so as we can see that the model with the grounding consistently outperform model without the grounding. And what's interesting is that the model with the grounding at the 10K steps already achieve better performance with the model without the grounding, like with the 10 times more steps. And we also did various study predictors of using the linguistic, visual, and the psycholinguistic models factors to predict model behavior, which I don't really have time to talk about here, but I'll be happy to talk offline. And what this work tells us is the grounding ability acquired from pre-training facilitates fast learning and fast mapping and learning new words without explicit supervision, and we need to take grounding seriously. So this also provides the insight to the 3D grounding. So these cognitive robots, they operate in a 3D environment. So the ability for them to understand and learn language to this 3D environment is important. So to address this problem that by my student Jed Yang and Xu Hejie, in collaboration with David Hejie, we created this million scale data set for 3D LLM. So this data set is the largest compared to other 3D data sets with 40K 3D rooms, over 6 million densely grounded 3D and text pairs, and built based on a variety of tasks. But what I want to say is that the dense annotation can be daunting. If we have a human do all these, so let's say each data point will take 5 minutes because they have to generate long descriptions and also ground these linguistic expressions to the bounding boxes. And if the person works around the clock, it will take 5 years. If the minimum wage is $10, it will cost $500,000 more than that to create this data set. But what we have today is the advances in AI. With these, we can leverage these large language models to automatically curate this data set. So here just some statistic here. We use the GPT-4, and it costs 2 days with $3,000. And if we use the GPT-4o, it will cut down the cost by 50%. And you may also wondering, what about the quality of the data? And we did an extensive study, human study, to evaluate the quality of the data. So if you are interested, please come to the poster. Well, you see the human evaluation. You're also gonna see how these models trained on this data can significantly reduce the hallucination in vision language models. Okay, so the second story I'm going to talk about is the language use. That we can use language to empower embodied AI in the context of task learning. And it's just another quick advertisement again, because I have students here. We're going to give demos and posters later on. So in this recent work, we're looking at how to use language to teach embodied offline RL agents to learn tasks. And so here we have, informative, I don't have time to talk about here, but our studies have shown that the rich language we use, if we use rich language, we can actually improve the learning outcome of these RL agents. And if you're interested about, what do we mean by informativeness? What do we mean by diversity? Please also come to the poster session. So what I want to say a few words is using the language to learn the object manipulation. So transformer-based models have been used to learn the visual motor policy for robot manipulation. So for example, this work, RVT model, was developed by NVIDIA from Dieter's group. So Dieter gonna be here giving a keynote in the afternoon. So this model is a multi-view transformer for 3D manipulation. It achieved the state-of-the-art performance in terms of both speed and text success at the inference time. So it's really cool. But the world is full of uncertainties. World is dynamic. When we apply these type of models to the world at inference time, inevitably, we're going to encounter some failures. So for example, in this case, the task closed the navy jar, and the arm just somehow stuck, when picking up the lid, and it didn't move to the jar. And in this case, slide the block to green target, the arm, moved to the wrong direction, so it would fail. And in this case, stack the wine bottle to the rack, and it's just knocked down the bottle, and the task failed. So one of the important questions is, how do we provide some sort of a mechanism to allow these models to learn to prevent failure before they happen or recover from failure? That's an important question. So this very recent work, we use the rich language we use the rich language to guide a model to learn failure recovery policy. So this work is led by my student Yingpei Dai and Jaejun Lee, and also Nima, collaboration with the Nima Fazali from the robotics department. And so what will be the solution, right? So one possible solution is just humans in the loop. What if when the exception happens, we have a human monitor the situation and give the language instructions? Yes, this works. People have looked at that. Recent work have given this like a simple language instruction at the inference time. So these language instructions from the recent work are simple in the sense that they are usually 4 to 5 words long, and they have like probably one semantic row. Semantic row is we often use semantic rows to measure the amount of information in the conveyed in instruction, like expressed by verbs, such as velocity, manner, distance, direction, and so on. So on average, these instructions give one aspect of information. But from our earlier work, I didn't get to talk here, we found that rich language use can improve task learning. And in this case, rich language use means that we can give language feedback about what went wrong, and also give feedback about what should be done next. And that's okay, but the one problem here is it is not realistic in reality to have humans sitting there constantly monitor the situation and give these kind of feedback. So our solution is, what about AI in the loop? So we have an AI supervisor that would monitor the situation and generate these instructions. And then the actor, which is built on top of the RVT, will learn these, the visual model policy to take the instruction and take the observation to generate action trajectory. So then the one question is, where does the training data coming from? So we developed this data set, again, by leveraging the generative AI, large language models, and generate this data set, rich language to guide failure recovery. And this data set, we use the simulated data in the RL benchmark, and as well as the Panda robot from Nima's lab. And the language we have is much richer, and the length, average is about 18 words, and it can specify different aspects of information, like 3 to 3.6 on average, the semantic rows. And so here, I just want to show a couple of videos, because the demo, you won't be able to see it, is, for example, the task here is to put the Oreo on the top shelf. Okay, so this is the failed case at the inference time, the first. And the simple language is we also have the model variations where we only give the simple language instructions. So here the VLM is the supervisor that grabs the just very simple language, and also can see the field. And this one is with rich language. So you can see VLM generates longer descriptions. Okay, so so this one succeed. And what's really also nice about this infrastructure framework is that in situations that we really need human intervention, human can just simply give language instruction. There is no need for further training. So the model itself, we can just directly use that for human intervention. And here is just the video to show, in this case, that just by using the razor itself still failed. But here is, you can see that the VLM generates the instruction, and at some point, see that now this is human give the instruction. Okay, so the VLM and the human can work together to help a model prevent a failure. All right, so if you want to know more about the data augmentation pipeline, and also the comprehensive results on the generalizability and adaptation to new tasks, as well as sim to real, please join us at the poster as well. Okay, so very last, I just want to say a few words about that's a language use for task learning, but language use also can help facilitate collaboration. So theory of mind, many of us have heard of that. So it's about intellectual abilities that we humans have that enables us to understand that others also have beliefs, desires, plans, hopes, and so on that may differ from our own. And we use theory of mind a lot. For example, in language communication, when I use language to communicate to a child versus to an adult, my choice of words will be different because I take the knowledge of my audience, listener, into consideration to generate language. And it's used, in our collaboration. So the question here is, can we model theory of mind for these embodied agents when they communicate with each other in collaborative tasks? So this is a joint work with former PhD students, Paul, and former undergrad, now is a PhD student at Columbia, Sky. So we look at this problem, and we actually use the Minecraft to study this. We call it Mindcraft. So as you can see here, this is third-person view. So the two players, they each give given some plans. So they only have a partial knowledge about how to accomplish the knowledge about partial plans. But they don't know, what each other's partial plans about. So they have to communicate, collaborate with each other to accomplish shared goal. So as you can see, these players, they can communicate, they can act, they can move around to build these blocks together. And one important feature about our platform is that because theory of mind is latent, we would not be able to know, right? So this platform periodically throughout the interaction asks questions, about the partners, about their beliefs. So these questions appeared if we ask one partner, like, has the other player made some block until now? Then we ask the other partner, have you made some block now? So the power is, this paired questions allow us to have some measurement of a common ground. So we have questions about task status, knowledge, and what partners currently doing. So we have the human studies here, and we can see this is what humans do. They're consistently very high in terms of predicting about each other's task status, and the knowledge, and about what others doing is increasing weak at the beginning, but become better as the conversation unfolds. And we also just developed, replaced the human with the AI agent. And as we can see that in terms of understanding partners' task status is still similar to human, relatively flat, and the knowledge is also similar, even though it's a little more volatile. But then about partner's current task is kind of falling apart. So, but this tells us that we have the agent can actually proactively ask if they cannot really predict what a partner is currently doing. So very quickly, very last, and Stella mentioned that, is I want to share this. The one highlight of our journey is that last year we won this Amazon Alexa Symbot challenge. So this is the challenge where the university teams are tasked to develop simulated robots, basically robots in a simulated environment that can collaborate with human and follow instructions. And Amazon customers can interact with these the robots through this echo display. Okay, so I just show a
what do we do now?
Quick snippet.
Pour some cereal into the bowl.
Okay, let's pour cereal into the bowl. Awesome. We have now poured cereal into the bowl. What do we do next?
So, yeah, I'm not going to show the whole video here. What I want to say is what's really unique about this challenge is that when we develop systems in the lab, we really had the opportunity to have the system interact with people in the wild. But Amazon, this challenge, provides this opportunity, made it happen for us. So through our system was deployed through 5 months of deployment. We logged tens of thousands of user sessions on our interacting with our system, so we can have these different get this different statistics that we're not going into detail. But we have learned just so much from interacting with the real users, and we learned that to have these fully flexible conversation with embodied agents in the simulated environment still remains a challenging problem. But imagine one day we want to enable this with the real robots. We still have a lot of work to do. So I'd like to conclude that we have never been in a better position to study language and embodied AI. I'm very excited about the journey ahead. I'm excited about the foundations of a sensory motor grounded, cognitive motivated, and pragmatic rich language processing. I'm very excited about their implications in symbiotic communication between humans and agents, as well as their applications in our society. So last but not the least, so these are the wonderful students worked in my lab. This picture was taken maybe a year ago, so it's a bit dated. But I like to invite those students who worked in my lab, in whatever capacity. Could you please stand up? Don't be shy, don't be shy. So, yes. So these are the students who are really pushing the boundaries in this space. And it's their dedication that make my job fun and exciting. And so they're going to present posters later on, and please seek them out, and also seek me out if you have any questions about our work. And with that, thank you for your attention, and I'll be happy to take questions. Thank you for the question. Yes, so in fact, today, we have the language embedding. So now the language, the symbols all become the continuous vectors in the space. And this is very exciting in the sense that we can have signals from the multiple channels all come together in this joint space. And with that, we can actually develop models where language can influence different tasks that the different kind of reasoning and the embodied tasks.
Do you think it's possible to use another kind of signal, for example, the other kind of sensor, like the physical force sensor or the vision information to supervise the decision making of the AI?
Yes, I mean this. There's a lot of actually feedback from the environment that would allow us, give us signals, right, to train these models. Not just the explicit language feedback. In fact, a lot of these RL-based agents, they just let the agent go, to the world and just look at whether they can succeed in the task or fail the task and get these sort of signals and use that to train the models. So we have a variety of feedbacks from the environment, from our partners that would allow the agent to learn tasks.
Great.
Thank you.
Thank you. Our next talk is given by our next rising star, Hejie. She got her PhD from Emory University. She's now a postdoc at Stanford University, working on large language models and its applications to healthcare. She's well published in many top venues in machine learning AI for health, and she was named a rising star in electrical engineering and computer science last year. Welcome, Hejie.
Thank you. Hi. Thanks for the introduction. And I'm Hejie Cui, and thanks everyone for joining me today on my topic about towards trustworthy large language models adaptation and evaluation for healthcare. And I'm excited to share our insights and research with all of you. So in the next 10 minutes, I will cover 4 items. I'll start with the motivation on evaluating large language models for healthcare. I'll show you some contrast versus in reality versus language model uses studied in the literature. And then I will introduce our solution, MedBenchGen, which is a configurable benchmark generation system for health AI evaluation. And I'll also show some pilot study results on synthetic instruction generation and instruction tuning. And then I'll go through a use case that is really deployed at Stanford Healthcare called Chat EHR. And then I'll conclude with some key takeaways. So integration of large language models in healthcare is a topic that is of great interest and promise in the whole field. But when we look at how does the language model is really used in reality versus what is portrayed in literature, you'll find a great difference between those use cases. So this chart shows you the real analysis from SecureGPT, which is a GPT endpoint deployed at Stanford Medical for clinicians' access about their top use cases in their daily life versus the healthcare tasks that from the literature review. And you can see that in the left panel, the top uses of language models in reality are usually very practical and is more straightforward compared with the more difficult reasoning tasks reported in the literature review. And this figure shows more in detail the top uses. And so basically, this indicates a significant gap on how do we design the evaluation for large language models if we step out of the literature review and what people are chasing the benchmark for. So the challenges in the current healthcare AI evaluation is that, first of all, we have been using inappropriate benchmarks such as United States medical licensing examination, which definitely covers a lot of medical knowledge, but it reflects poor representations of real-world clinical settings. And you can see from the previous analysis, the daily usage is more like patient focusing and focus on the efficiency and improve the communication part. So it's different from like a medical reasoning task or purely focus on diagnosis or asking about the medical knowledge. So basically, it's like trying to judge a chief's ability to run a restaurant by letting them taking an cooking theory exam, which definitely reflects their knowledge, but does not necessarily translate to their practical ability to do a thing in the real setting. And the second insights we have identified is that current evaluation usually fails to specify the expected benefits to be verified. So without this clarity, it's difficult to find out whether an AI system is really improved the performance of in the real world setting versus it achieves good performance on arbitrary metrics. And from these three key stages in health AI deployment, we think the critical gap here is the need for building representative data sets for a specific clinical purpose. And manually creating such data sets from scratch is resource intensive and of high cost. So I will introduce our solution about MapBenchGen, which we definitely want to give it a better name. It's still ongoing work. So this benchmark aims to generate a configurable novel benchmark that do not currently exist for evaluating healthcare AI. And we designed this system to make it configurable from three different perspectives. On patient-wise, we want it to, on the patient demographics, such as gender and race. And from the clinician's perspective, we will include the specialty value spectrum, where you can specialize visitor records from a specific disease or a community. And on the evaluation task, which I will touch base more in the next few slides, that will really dive into the real world cases we want to evaluate as the target tasks. So as a pilot study for creating such evaluation benchmark data sets, we designed, we investigate the instruction response data generation from EHR for instruction tuning a large language model towards healthcare domain. And basically, we start from patient records. EHR represent electronic health records, which is basically all the events that happens during per patient visits in the hospital. And then we prompt our large language model with crafted prompts to generate instruction response pairs that covers different real-world healthcare tasks. And then we use this instruction response data to fine-tune or instruction tune a local large language model. And we then, we also do the data selection using preference data to really select the high-quality data for model training. And with this instruction tuning model, we can evaluate it on existing benchmark such as MMU clinical or standard classification tasks on risk prediction. And we also can build more relevant evaluation data sets from the generation paradigm. And to define the top real-world evaluation tasks, we look into different resources from the intersection of the four scenarios. So first of all is human crafted annotated instruction data sets, which is actually collected from clinicians of 11 specialty values that reflects their everyday routine from the interaction with EHR. And we also look into the clinical reviews on healthcare application with LLMs and the Secure GPT log portal where we can get the clinician's interaction with ChatGPT. And also the Chat EHR use cases, which is an app built and deployed at Stanford Healthcare. And those are the 5 most representative evaluation tasks that we should pay attention to when building such healthcare AI evaluation system. And to show some concrete example, so here is given this task of information retrieval, summarization, and synthesize an instruction that generated from the system can be, please summarize the findings of the patient chest X-ray report from a particular date. And the response, as well as the rationale, are generated from the input of relevant EHR snippet and the rationale to ground these instructions and the response. And this is another example on clinical decision support diagnosis where the instructions is generated to ask about differential diagnosis. So a real-world use cases of such evaluation benchmark is the Chat EHR application at Stanford Healthcare. So it's essentially a search app for clinicians where the task is to help the clinicians find the citations in the patient records. And the interaction way is that given an input from like a query from clinician, the app will generate a relevant fragment from the electronic health records that can be evidence for the given query. And the current method that is really implemented and deployed in the app is to embed these queries and EHR trunks with GPT embedding model, and then perform some index search based on semantic similarity. And when we talk with the research IT team at Stanford Healthcare, the key issue they have is that there is no ground truth for evaluate the app returned search results for the clinician's query. So basically, there's no way to know how does the app performs besides they plan to collect some sum up data, sum down data for the evaluation results. And our solution here is to provide a proxy benchmark evaluation set where we can, given a specific patient timeline trunks, generate an instruction, then we use these pairs as a proxy for ground truth data, where you can evaluate the search engine's ability on retrieving the original trunks given the generated instructions. So my key takeaways here is to, in terms of bridging the evaluation gap, we must align health LLM evaluation with real-world clinical needs, and this helps us to build AI system that is not only academic sound, but also practically useful in the real-world setting. And the second part is the synthetic instruction generation can potentially narrow the divide between academic research and clinical applications. And this will enable us to generate more relevant evaluation benchmarks that can be useful for the real evaluation. And some future direction, including to study multimodal instruction tuning using this more resource contain the medical imaging and time series data included in the records. And also we find out that the complex reasoning data sets there's still some gap there. So how to enhance LLM's ability to handle more nuanced multi-step medical reasoning, it could be an interesting direction. Yeah. That is my talk, and I'm happy to take questions.